A step-down transformer is a device used to reduce the voltage of an alternating current (AC) electrical signal. It has a higher number of turns in the primary coil input side than in the secondary coil output side, resulting in a lower voltage output compared to the input voltage. Here's a simplified explanation of how a step-down transformer works. The construction of a step-down transformer typically involves the following components. Core. The transformer core is made of a high-permeability material, such as laminated iron or steel, that provides a path for magnetic flux. It is typically constructed in the form of thin laminations stacked together to minimize eddy current losses. Primary coil. The primary coil, also known as the input coil or winding, is typically made of copper wire wound around one side of the transformer core. The number of turns in the primary coil determines the voltage ratio between the input and output. Secondary coil. The secondary coil, also called the output coil or winding, is wound around the other side of the transformer core. It consists of a different number of turns compared to the primary coil to achieve the desired voltage reduction. Insulation. Insulating materials, such as varnish or enamel, are applied to the wires of the primary and secondary coils to prevent electrical short circuits between adjacent turns and layers. Terminals. The ends of the primary and secondary coils are brought out as terminals for connection to the power source and load, respectively. These terminals allow the transfer of electrical energy between the transformer and the connected devices. Enclosure. In some cases, transformers are housed in an enclosure to provide protection against physical damage, dust, moisture, and other environmental factors. The enclosure can be made of materials like plastic, metal, or fiberglass. It's worth noting that the actual construction of transformers can vary depending on factors such as the power rating, voltage levels, and specific application requirements. Higher power transformers may include additional features such as cooling systems, tap changers for voltage adjustment, and protective devices like fuses or circuit breakers. Turns ratio. The turns ratio of a transformer is defined as the ratio of the number of turns in the secondary coil, Ns, to the number of turns in the primary coil, Np. It determines the voltage transformation between the input and output sides of the transformer. Mathematically, the turns ratio, TR, is expressed as TR equals Ns/Np. For a step-down transformer, the turns ratio is less than 1, indicating that the secondary coil has fewer turns than the primary coil. This results in a lower output voltage compared to the input voltage. For example, if the turns ratio is 1:2, it means that there are 2 turns in the secondary coil for every 1 turn in the primary coil. In this case, the output voltage will be half of the input voltage. Similarly, a turns ratio of 1:3 would result in an output voltage that is 1/3 of the input voltage, and so on. The turns ratio directly affects the voltage transformation capability of the transformer. By varying the turns ratio, transformers can step up or step down the input voltage to meet the requirements of different electrical systems and devices. Voltage transformation. Voltage transformation is the process by which a transformer changes the voltage level of an electrical signal. A transformer can either step up or step down the input voltage depending on the turns ratio of the primary and secondary coils. When an alternating current, AC, voltage is applied to the primary coil of a transformer, it generates a magnetic field in the iron core. This magnetic field then induces a voltage in the secondary coil based on Faraday's law of electromagnetic induction. The induced voltage in the secondary coil is directly proportional to the turns ratio between the primary and secondary coils. For a step-down transformer, the primary coil has a higher number of turns compared to the secondary coil. The input voltage is applied to the primary coil. The induced voltage in the secondary coil is lower than the input voltage. The output voltage is determined by the turns ratio and can be calculated using the formula Vout equals N2/N1*Vin, where Vout is the output voltage, N2 is the number of turns in the secondary coil, N1 is the number of turns in the primary coil, and Vin is the input voltage. For a step-up transformer, the primary coil has a lower number of turns compared to the secondary coil. The input voltage is applied to the primary coil. The induced voltage in the secondary coil is higher than the input voltage. The output voltage is determined by the turns ratio and can be calculated using the same formula as above. Transformers are widely used in electrical power transmission and distribution systems to step up the voltage for long-distance transmission and step it down for utilization in homes and industries. They provide efficient and convenient voltage transformation without changing the frequency of the electrical signal. Voltage output. The voltage output of a transformer is the voltage produced across the secondary coil of the transformer when an input voltage is applied to the primary coil. The voltage output is determined by the turns ratio between the primary and secondary coils. In a step-down transformer, where the turns ratio is less than 1, the voltage output is lower than the input voltage. The relationship between the input voltage, VIN, output voltage, VOUT, and turns ratio, TR, can be expressed by the formula VOUT equals NS/NP * VIN, where NS is the number of turns in the secondary coil and NP is the number of turns in the primary coil. For example, let's say we have a step-down transformer with a turns ratio of 1:2 and an input voltage of 120 volts, VIN. Using the formula above, we can calculate the voltage output. VOUT equals 1/2 * 120 is equal to 60 volts. So, in this example, the voltage output of the transformer would be 60 volts. Conversely, in a step-up transformer, where the turns ratio is greater than 1, the voltage output is higher than the input voltage. The same formula can be used to calculate the voltage output based on the turns ratio and input voltage. It's important to note that this calculation assumes an ideal transformer without losses. In real-world scenarios, transformers may have some losses, such as resistive losses and magnetic core losses, which can slightly affect the actual voltage output. Power transfer. Power transfer in a transformer refers to the transfer of electrical power from the primary coil to the secondary coil. It involves the conversion of voltage and current levels while maintaining the same power level, disregarding losses in the transformer. The power transfer in a transformer can be described using the following equation. Power input, PIN, equals power output, POUT. Mathematically, the power can be calculated using the formulas. PIN equals VIN * IN. POUT equals VOUT * IOUT. Where VIN is the input voltage, IN is the input current, VOUT is the output voltage, and IOUT is the output current. In an ideal transformer, where there are no losses, the power input is equal to the power output. Therefore, we can say VIN * IN equals VOUT * IOUT. Based on the turns ratio, TR, between the primary and secondary coils, the relationship between voltage and current can be determined. VOUT equals VIN/TR. IOUT equals IN * TR. Substituting these relationships into the power equation, we have VIN * IN equals VIN/TR IN * TR. Simplifying the equation, we get IN * VIN equals IN * VIN. This equation confirms that, in an ideal transformer, the power input is equal to the power output. It's important to note that real transformers have losses due to factors like resistive losses in the coils and magnetic core losses. These losses result in a slightly lower power output compared to the power input. Therefore, the actual power transfer efficiency of a transformer is typically less than 100%. Step-down transformers are commonly used in various applications, including power distribution systems, electrical appliances, electronic devices, and industrial equipment, where lower voltages are required for safe and efficient operation.